Hello, everybody. Welcome to our first session of the European Quantum Software Institute Colloquium. It's a great pleasure to have Agnes Montanaro here with us to inaugurate that series. Since it's our first session, let me just give you a very brief introduction to what is AXI. So let me share my slide. So the European Quantum Software Institute is an initiative from 6 research centers in Europe. So there's the Paris Center for Quantum Computation, the Portuguese Quantum Institute, QMath in Copenhagen, QSoft in Amsterdam, the Technical University of Munich, and the University of Latvia. So here you can see where we are located, and this in fact corresponds to the initiative of these 6 colleagues, from left to right: Matthias Christandel from Copenhagen, Robert König from Munich, Jordanis Kerenidis from Paris, they are here, and Harry Burman who from Amsterdam, who's on a train, myself, and Andris Ambainis from Riga, who unfortunately could not be here today. He's actually the organizer of our colloquium, so I'm just standing in for him today, but he will be hosting the colloquium, which he organized already, this one, from the future. So we are very excited to launch this initiative and to have this series of colloquia and other events, which we'll announce in the end. Actually, I still have this slide. So we have a website that is still being set up. So that link is still not working today, but we hope later in the week. You can also follow this Twitter account, which Andris set up, and save the date for the first AXI workshop taking place in the 2nd of May this year in Paris, and we'll have a seminar and next sessions of the colloquium, which we'll announce at the end. So thanks everybody for joining. We currently have more than 65 people online and still joining. So let us start. Again, it's a great pleasure to welcome Agnes Montanaro from the University of Bristol and also from the company Phasecraft. So Agnes Montanaro has had many important contributions to quantum algorithms, complexity theory, both classical and quantum, and contributing to the development of what we now call quantum software. So it's really, we are very honored to have you, Agnes, here to inaugurate our colloquium series. So please, the floor is yours.
Brilliant. Thank you very much for this kind introduction, and also for the very kind invitation to speak to you all today. It's fantastic to see so many friends here and so many new people as well to meet. And indeed, I'm going to try to tell you something today about near-term quantum algorithms for optimization. I'm going to share my screen in a second, and I should say that I guess I may not see when people stick their hand up or something after that point. So from my point of view, it's absolutely fine if people want to jump in and ask questions throughout.
Well, I'll keep an eye on those.
Okay, fantastic. Thank you. So indeed, I will share my slides. Hopefully this works. Hopefully you can now see my
Yes, we can.
Slide. Great. So, right. So what I'm going to talk about today is based on 2 papers, both of which are joint work with my PhD student, Sami Boulebnane, and one of them is joint work with a team from Roche. And you know, both of these papers are joint work with Sami, and as is traditional in these cases, the PhD student did all the work, and as is perhaps not always traditional, the PhD student, in this case Sami, was also responsible for the vast majority of ideas in both of these works. So I'd like to thank Sami very much, and what you're going to be getting today is sort of my take on some of the ideas that he developed primarily in these papers. And indeed, both of these papers are work that was done at Phasecraft, and the goal of Phasecraft is to develop quantum algorithms for near-term quantum computers. So the kind of quantum computers that we have now, or perhaps might have in the next few years' time. And in this, the case of these papers, we were particularly interested in what we might be able to do in terms of problems that look not like simulation of quantum systems or something like that, but problems which look like optimization or constraint satisfaction problems. So problems that kind of have more of a computer science flavor rather than a physics flavor. And that's what I want to talk about today. And I want to look at 2 particular problem domains. One of them is a sort of very famous and fundamental problem in computer science called boolean satisfiability. And in this problem, we're looking to find a solution to a set of constraints on Boolean variables x1 through xn. So this is of the form that I've shown here on this slide. We have a bunch of clauses, like here this first thing in the brackets, x1 or x2 or x3 is a clause. Then we've got not x1 or x4 or x7. Then we've got x2 or not x5 or not x7. And the idea is that this clause is satisfied if it evaluates to true. So for example, if the first bit x1 is 1 or true, or x2 is true, or x3 is true. And this clause in itself is sort of easy to satisfy. We can just choose anything that assigns at least one of them value 1. But what's not so easy to do is to satisfy all of the clauses together. And this can be very complicated. This problem's NP complete in full generality. So we expect that there's no efficient classical or quantum algorithm for solving this problem. But we can still ask the question of, what is the complexity of solving this problem? Like, if it is an exponential time complexity, like what is the exponent? How quickly can we solve this? And one can ask this question sort of in the worst case, like what's the worst case complexity of solving this problem of an instance of size n? But one can also ask about the average case. So in this talk, I'm going to be thinking about a problem called random KSAT, which I guess I'll define a little bit more in a minute, where we are choosing the formula that we're looking at random. And we're interested in the sort of average case complexity of this. So if we choose this this input Boolean formula at random, how much time does it take us to find a solution to this problem, to find an assignment of zeros and ones to these variables such that the whole formula evaluates to true, if indeed there is such an assignment, which there might not be. In that case, I guess we have to output that there is no satisfying assignment. So I'm particularly going to be focusing on this so-called random KSAT problem, where the clauses in this formula are all of length k, and they're picked at random from the space of all such clauses. So we just produce a formula by choosing how many clauses we have, which is usually going to be some kind of constant multiple of the number of variables. And then we're choosing each clause uniformly at random, and then that's our problem instance. And then we're interested in finding a satisfying assignment to all of those clauses. And this, in itself, this may not look like an especially practically relevant problem, because we're just choosing the problem at random. We're not choosing it to be one we particularly care about in terms of some problem we genuinely want to solve. But the point is that this might help us to understand, at least over this family of instances, whether quantum algorithms outperform classical ones. So this is a sort of good test case, perhaps, for the power of quantum algorithms versus classical algorithms. We can try and work out for these randomly generated problems whether they perform better or not. And I'm going to be looking at this in the particular case of this near-term quantum algorithms for solving this problem, for finding a satisfying assignment. Okay, so that's one problem. And the other one is one which comes from a different domain, which is, I guess, pharmacology or like bioscience, and it's the protein folding problem. So here in this problem, we're trying to predict the spatial structure of a protein given its sequence of amino acids. So we are given a protein that's described as a long string, sort of somehow a 1D object, if you like. And we're trying to understand how this thing folds into the right position in 3D. And this is something that's been quite prominent recently, this problem. It's been in the news a bit. There's been some very impressive developments here. But again, this is somehow can be seen as an optimization and also a constraint satisfaction problem, in that we're trying to find the lowest energy state of this protein. So we're imagining that different configurations of the protein will have different energies, and we're trying to find the configuration of the protein which produces the lowest energy in 3D. I'm not going to talk about this so much, actually. I'm only going to mention it a bit at the end of this talk. And I'm going to focus on a particular part of the paper that we did on this, which is just looking at small scale examples of the protein folding problem and trying to compare quantum and classical algorithms for that.
So Ashley, there's
Yes.
a question in the chat. Do you want to keep it for the end, or shall I read it now?
I can just look at the chat. Thank you. I just spotted that. Okay, so I guess the question is about use cases of case-out problems in practice. So one that I like is electronic design automation, where somehow maybe you have an electronic circuit and you want to understand if there's a fault in the circuit. You want to understand if it's sort of producing the right answer or not. And sometimes you might be able to do this by plugging in some sort of zeros and one, like you basically want to know if there is a sequence of zeros and ones that you plug into the circuit such that some output of the circuit is not what it should be. Like, I mean, maybe you can sort of check the outputs of the circuit in one way or the other, or maybe you even have some line of the circuit which pops out with fault or something in the end. So then, you can convert such an electronic circuit into a formula in logic, like in the conjunctive norm form, like the one on this slide. And then if there is, perhaps if there's a solution to that formula, you can make that correspond to if there's a fault in the circuit. So this can help you find faults in an electronic circuit. That was extremely high level, but this is a sort of very fundamental NP-complete problem. And in fact, you can reduce many problems of practical interest to this form. Okay, I guess I will move on. So now I want to introduce the quantum algorithm that I'm going to be talking about today, which is quite a well-known one for these near-term quantum applications, called QAOA, or the quantum approximate optimization algorithm. And this has become extremely prominent since some groundbreaking work of Fahy, Goldstone, and Gutman in 2014. But in fact, a very similar algorithm was introduced by Tad Hogg back in 2000. The chief difference being that in Hogg's work, he was looking at a particular choice of parameters for the algorithm, whereas the Fahy, Goldstone, and Gutman paper, they introduced the idea of optimizing over these parameters variationally. But the key idea in the algorithm is that, which many of you probably are familiar with, is that we start in a state which is the uniform superposition over assignments of 0 or 1 to n bits. And then we alternate time evolution with one Hamiltonian and another Hamiltonian. And the first quantum Hamiltonian, or in fact, in this case, a classical Hamiltonian that we time evolve with, is this Hamiltonian HC here. And this is like a cost Hamiltonian. So the idea is it associates each bit string with a cost C of Z. So each bit string Z is associated with a cost C of Z. And so, for example, in the case of satisfiability, this cost might be the number of clauses which are not satisfied in the formula. So the idea is that this somehow represents how bad a particular solution is. And we time evolve with that cost Hamiltonian with time gamma 1 here, where this is gamma 1 is some parameter to be determined. And then after that, we time evolve with another Hamiltonian, which is a HB here. And this one is just some fairly simple one that does not depend on the particular problem instance. And in what people normally use in the case of QAOA is they have a Pauli X operator on each qubit. So just this is like written here as like XJ. And we're time evolving with this thing for time beta 1. So this is some other parameter beta 1. And then we're repeating this operation p times throughout this talk. P is always going to be the number of layers of this algorithm. And then in the end, we're just measuring in the computational basis and we get some answer. And the hope is that this is a good answer, which has low cost, or ideally the answer that has minimum cost. And the idea is that the operations in this algorithm are easily implementable as a quantum circuit. So this first one, this time evolution according to this cost Hamiltonian, you can do efficiently if you can calculate this cost function efficiently. And sometimes there are some very concise quantum circuits for certain cost functions which are sort of ultra simple to implement. For example, if this cost function splits up as a sum of individual cost functions that only depend on a few qubits, and that can make it even more efficient algorithm, which makes it sort of very tempting for near-term applications. Whereas this mixing operation, this time evolution according to HB, this is actually like a product unitary operation. It's product over all n qubits. So this is sort of very easy to do on a quantum computer. And the hope is that at the end of doing this process, if we measure, we get a sort of good answer, solution with low cost. And this depends on the choice of these parameters like gamma 1 through gamma p and beta 1 through beta p. And this is something that you can try to determine using some kind of optimization process using the quantum computer itself. So you measure and you get an answer that has some cost, and you want to optimize over these parameters beta 1 through beta p, gamma 1 through gamma p to minimize that cost. Or you can choose these parameters up front in some way, which is sort of a priori known to be good. And in fact, it's that sort of second approach I'll be focusing on more in this talk. Like, for a given choice of parameters, how can we work out whether we get a good answer, we get something that has low cost? And you might wonder, if you haven't seen this before, like why on earth we should think that this will give us something good, that it will be a good way of finding a low cost string Z. And there is some intuition that comes from the quantum adiabatic theorem for why this is true. And sometimes, though sort of rarely, it's provable that this is a good algorithm as well. But often, it can actually be really a challenge to work out what the behavior of this algorithm is and how well it performs. And this is something that we were trying to do in this work, try to work out for certain particular problems, ideally sort of theoretically, analytically, how well this algorithm performs, or if we could not do it theoretically, at least come up with some good numerical evidence. Okay. And in the case of KSAT, this Boolean satisfiability with k variables per clause, our cost function C of Z is going to be the number of violated clauses, so the number of clauses that we do not satisfy with a given input bit string. And a problem instance then is given by some of these clauses, sigma. So we've got sigma 0 is the first clause, through the way through to sigma m-1 is the mth clause. So we have m of these clauses. And our cost function is the number of clauses that are violated, the number of clauses that are not satisfied by a given bit string Z. And then our overall sort of cost Hamiltonian is just the sum over projectors over onto Z of that cost of Z multiplied by the projector onto Z. Okay, so that's how we can apply QAOA to KSAT. And this is quite nice because each of these costs, each of these clauses only depends on k bits. So that means that we can implement this time evolution by this Hamiltonian H of sigma using an algorithm where the sort of gates, or like the operations in the algorithm, only depend on k qubits. And in fact, they sort of look very simple. They're like some kind of Toffoli gate that only depends on k qubits. So this is quite nice. And what we're interested in today is maximizing the success probability of this algorithm. So we want to maximize the probability of getting something that has zero cost at the end of this process. So this is given by this expression here. So often in QAOA, people look at minimizing the cost or maximizing the number of satisfied constraints. But here we're primarily interested in the probability of finding a satisfying assignment, which is this thing here. And that's the thing that we're going to try to study. Okay, and what we're interested in particular is random KSAT. So this is saying that, okay, we're fixing the number of variables n, and then we're looking at a number of clauses m, which is equal to r times by n. No, sorry, I should rephrase that. We're looking at choosing instances at random where the expected number of clauses is r times by n for some fixed ratio r. And the way we're choosing an instance of random KSAT is that actually we're choosing the number of clauses as based on a Poisson distribution, with that m being the expected number of clauses. And then once we've chosen the number of clauses, we are choosing each clause uniformly at random from the space of all allowed clauses. So we're choosing the variables at random and also the negations within that clause at random. So this is somehow a sort of super random instance of KSAT. And what we then have is we're able to come up with a result about the expected scaling of KSATs, of QAOA applied to random KSAT. And this is given on this slide, and maybe it's a bit of a mouthful, but I'll just try and go through it. So, okay, firstly, there's the condition that we have to have K being a power of 2. That's a technical restriction of our results. We don't believe it's sort of fundamental, but that's something which we need for our result to hold. And then we've got a number of layers of the QAOA circuit, which is P, and this can be arbitrary, but we're assuming that it's fixed, so it doesn't depend on the instance size n. And we've got some parameters of the QAOA algorithm, which again are fixed. So there's some condition on what the gamma parameters have to look like, which I'm going to defer to the paper, but there is some condition on how big the gamma parameters can be. There's no condition on what the beta parameters can be. They can be anything, but they have to be fixed. Then what we can say is that the success probability of QAOA averaged over random KSAT instances from this distribution that I mentioned above, the success probability of this thing, then taken to the log and divided by n, this thing exists. So this thing then we expect to be a number, I should say in advance. Like we're expecting that the success probability of QAOA with a certain number of layers for random KSAT is going to be of the form 2 to the minus alpha times by n for some alpha. And what this result allows us to do is compute what alpha should be. It allows us to compute the constant that's in the exponent. And the result says that firstly, this thing exists, and secondly, that we can compute it. And the way that we can compute it is in terms of the fixed point of some function of about 4 to the p complex variables. So it's a fixed point of a function of a number of variables that increases exponentially with p. And the and like once we've got this, if we want, once we have this number that we've computed, which is the success probability for the exponent of the success probability for given parameters beta and gamma, if we want, we can actually use this as a as input to optimizing the success probability over beta and gamma. So if we want to find the optimal beta and gamma for maximizing the success probability, we can do this by maximizing this classical proxy without needing to use the quantum computer at all. Okay, because I mean, often people think of QAOA as needing you use the quantum computer to optimize this beta and gamma, but this result says that for random KSATs, if you're interested in the average success probability over everything, then you don't need to do this. You can use this sort of analytical result. Okay, so I want to say a very little bit about the proof techniques that go into this result. And this was the most technical part of the paper, so this is really going to be a very brief sketch, and you can take a look at the paper if you want to learn more. But basically, the result that we come up with can be seen as a generalization of the sort of binomial theorem, which maybe many of you are familiar with. So basically, if we have a sum that has some binomial coefficients, which I've written in this sort of suggestive form here, like n choose n0, n1, whereas normally we would say that n1 is equal to n minus n0 here when writing a binomial coefficient, but I've written it in this slightly sort of unusual way here. If we have a sum that looks like this, we have a sum over n0 and n1 that sum up to n for some integer n. We have n choose n0 on normal notation, or in my notation, n choose n0, n1. Then we have some b0 and b1, which are just numbers. Then b0 is raised to the power n0, b1 is raised to the power n1. Then if we have a sum like this, then this is just equal to b0 plus b1 to the power of n. And this is, well-known result. It's not difficult to, I guess, to convince yourself of. And one could generalize this to a multinomial sum, where you've got this notation now here, which is saying that we've got, n choose like n0, n1, n2, dot, dot, dot. And again, these things are supposed to sum up to n. And this is just defined to be like n factorial divided by the product of the factorials of the things in this set. So if we have a sum that's of this form now, so it's like a generalization of the one above, this is just equal to the sum of these bs's to the power of n. So again, this may be sort of believable or something you can kind of convince yourself of. But it turns out that these sums occur in the context of the success probability of QAOA, but in a more sort of complicated form that one has to deal with. And in particular, the success probability of random k-sats, QAOA, when applied to average instances of random k-sat. So this is like the average success probability averaged over all instances of random k-sat. This turns out to take the form of some kind of generalized version of the multinomial sum on the previous slide. So for example, if we take k equals 2, so this is QAOA applied to random 2 sats, which is easy to solve classically. So this is just a sort of test example. So this one actually has a polytime classical algorithm, but interestingly, QAOA is not polytime when applied to this. So it turns out that the success probability of QAOA can be written as something that looks like a multinomial sum at the start, like on the previous slide. But then there's something else here, which is not so nice. And this is exponential of something that looks like a sum over some set A of some numbers, C alpha, and of something times the C alpha times by this not very nice thing squared. And this also depends on some numbers, A alpha S. And these numbers A and C, these coefficients A and C, they depend on the parameters of QAOA. And I guess also these BS's do as well. So this vector BS and this C alpha and this A alpha S, these all depend on what the parameters are that go into QAOA in a not very nice way that I'm not going to show here. And to work out how well QAOA performs, we need to basically evaluate this sum. And in some recent work by João Basso and co-authors, they proposed an algorithm to do something sort of similar but a bit different, with a different family of multinomial sums. But so our task is to evaluate this. And basically the thing in a sense that's hardest to deal with in this sum is the square here that occurs in this exponent. And what we can do is we can actually get rid of this using a nice trick involving sort of a Gaussian integration, where if we start out with this original thing here, if we write this as the expectation over, we can write this as the expectation over parameters theta alpha, which are chosen according to the normal distribution with some particular scaling. We can write as the expectation over theta alpha of this thing here, where now we've got rid of the square, but we've got this theta alpha in the exponent. There's also been some other sort of changes to these parameters that we've got, like square root of C alpha, and we've got a square root of n in here at the front. So this is a nice trick that somehow means that the square has gone away, but now we need to deal with this theta alpha thing here. And this thing, we can now use this, basically the multinomial theorem, like the sort of standard multinomial theorem of the previous slides, to rewrite this more concisely in this way. And now if we write out the expectation in terms of these theta alphas, it just looks like this. And this thing here, all I've done is I've taken out this sum over alpha on the outside, and it ends up looking like a product. And now we've got something inside that's an exponential of something that's kind of horrible looking, to be honest. But somehow this is now a bit easier to treat, because what we've got is something that's looking like an average over, so this is like an average over a set of some parameters, like whose size is given by the set A, which is supposed to be a sort of small size. It doesn't scale with n, of something that's exponential in n times by something which again doesn't depend on n. It's some it's something that may depend on like p, the depth of the QAOA algorithm, but it doesn't scale with the problem size n. And the idea is that now we can use this method, which maybe some of you are familiar with, called the saddle point method. And the sort of very naive way, I guess, that I think about this method is that we can understand what this thing evaluates to just in terms of the maximum of this function here, in some sense. So we're imagining that n is going to infinity, and we're imagining that the size of this sets A and S is not going to infinity, it's sort of fixed. And that means that sort of intuitively, we might imagine that this thing will somehow be dominated by the value when this guy here and this thing in the brackets is biggest. And this intuition is, kind of dubious because this thing actually, is kind of complex valued and stuff like this. But nevertheless, one can churn through some calculations and use this to work out what the final scaling is. And, this was a super brief summary, which is not enough to really understand the argument, but in the paper, there's a more detailed sort of example, which is not the sort of full calculation for arbitrary KSAT, but it is a sort of simplified case, which might enable you to get a sense of how the method works. But okay, this then leads to the question of how well these analytic predictions match the empirical results. So what we did in these previous slides is work out an analytic argument for what the success probability should be for random KSATs on average as n goes to infinity. And one may wonder, firstly, whether the analytical result is correct, and secondly, if it actually is something which is meaningful for relatively small instance sizes n, or if it's something which only becomes meaningful as n really becomes gigantic, like too gigantic to even do in a reasonable time. So to test this out, we did some experiments, and we looked at how well QAOA performed empirically versus how well it performed analytically. And this is for very small problem sizes, as you can see, well, relatively small problem sizes in terms of the number of variables. In fact, the number of clauses is quite large in the formula because we're looking at 8 sat here, which turned out to be a sort of interesting regime. And what we saw is that the theoretical and numerical scalings actually matched very closely. So this is for different numbers of layers of QAOA P. And what we can see is that the scaling is very similar of both the theoretical and the numerical results. We don't necessarily expect the sort of the y-axis position of these lines to be the same, because the theoretical results actually don't give any information about what the overall sort of constant factor is in front of the scaling. So there's no necessarily reason to think that these lines will actually precisely match up in that respect, but it turns out that they do for most of these cases, and for larger numbers of layers P, we seem to have a sort of bit of a gap there, but at least the scaling is the same. So okay, so this gave us some confidence that the analytical results actually match up with the empirical average success probabilities. And then this led us to try to understand, how well does QAOA compare with classical algorithms now? In the end, what we were interested in is, does QAOA outperform best classical methods? So we looked at a number of different classical methods for solving KSAT formulae, random KSAT formulae. And we've evaluated quite a number of different solvers. The one that we found in our experiments to perform the best is one called WalkSat LM. So this is a modification of an algorithm called WalkSat, which maybe some of you are familiar with, to make it a bit higher performance. And it's been shown to perform very well for random KSAT instances in the past, and indeed that's what we found in our experiments too. And what we were interested in doing is working out how well QAOA did in terms of scaling, as opposed to precise performance on fixed size problems, which, or perhaps in classical simulations. We were interested in how well it performed in terms of scaling compared with these sort of classical competitors. And we looked at the different algorithms, and we looked at a number of different random instances, I think 10,000 or so. And we looked at the median running time of the algorithms on those instances. And you can see the results on the graph here and in this table. And basically the median running time, as you know, in the case of QAOA, this is just 1 over, for each instance, it's the running time on average is 1 over the success probability. So this is the median of that quantity taken over the instances we were looking at. And we were looking at QAOA with different numbers of layers. I've just shown a couple of different numbers of layers here, like 14 layers and 60 layers. We did a bunch of other experiments too. And we also considered a variant of QAOA where we took the standard QAOA algorithm and we then did we then applied this a random walk to it afterwards. We did we used the QAOA output as an input to a classical solver, which is based on doing a random walk called walksat. And you would expect it to have slightly better performance, which indeed is what we saw, but not perhaps significantly better performance. And what we see from these results is that QAOA with large enough numbers of layers seems to outperform walksat LM, which is one of the closest, which is the highest performance classical algorithm we looked at. And okay, so I can see a question about how running times are measured.
Yes.
So for some of the algorithms, like MapleSat and Glucose, the algorithm basically spits out the number of decisions made in the algorithm. So this is a sort of backtracking type algorithm, and we can get some information from that about the sort of number of steps in this tree that it expands. And you know, this we can actually correlate with the real world running time, and it turns out, you know, it does correlate quite nicely as well. So in the case of walksat LM, I think it was the empirical running time that was measured. For that, you could also potentially get a sort of more, I guess, a theoretically sort of precise measurement, because this is a random walk type algorithm, and you could perhaps look at the you know, the sort of mixing time of something of that that corresponding Markov chain. But I think this was a sort of an empirical result measured over sort of many runs. Yeah. Okay. Okay, so that's a question of, you know, looking at particular depths, how you know, particular depths of QAOA, how it compares with, you know, some of these leading classical algorithms. And then there's a question of, you know, how deep we'll need to go to outperform classical algorithms. I see there's a question about other comparisons. I might leave that to the end if that's okay, because I might have a couple of other things to say about that. And basically for this, we were looking at fitting the scaling with P of the running time to some function, and it turns out that a sort of power law fit seemed to be pretty good from our experiments. And there's a sort of interesting technical point here, because the average runtime of QAOA can be measured in sort of different ways. And in particular, like if you take the average success probability over all instances, which is the thing that we can control, if we take 1 over that, that will not necessarily, that's not actually the correct like average runtime, because the expectation of like 1 over x is not the same as 1 over the expectation of x. In particular, from our experiments, one can either look at the average of, sorry, let me rephrase that. One can either look at the 1 over the average probability, or one can look at the median running time, and you know, based on our sort of numerical experiments, and try to understand how the scaling of those things change as p increases. And we saw sort of different results for one compared with the other. And one reason for this might be that the best parameters for optimizing the running time, the best parameters for optimizing the average success probability may not be the best ones for optimizing the runtime. So basically, we have these sort of different lines here, and a sort of summary is that the red line is sort of, the red line and the green ones are sort of the more optimistic predictions, which are, what the scaling exponent might look like with P, in an ideal world for QAOA, whereas this, this dashed line here, the blue line, or even a sort of even more pessimistic one that goes kind of quite close to the, to this black dashed line, which is the Walks-LM performance. This is the sort of more pessimistic view one might take, which is, which would say that there's a sort of less significant improvement over Walks-LM, which is the black dashed line. So basically, we don't know where the performance of QAOA with large P really will lie, I think it's fair to say. Okay, so I guess, do I have just like a couple of minutes, yes, of this?
Sure, please. We want to leave some minutes for discussion, but please go ahead.
Yeah, okay, so maybe I'll just take 5 minutes to say something brief about the protein folding.
That's fine.
So really, this is a fundamental problem in computational biology, which many of you have probably seen. And we're given a protein described as a sequence of amino acids, and we're trying to predict the 3D configuration of this sequence when the protein sort of folds itself into 3D. And this is a very computationally hard problem, and it's one that's been studied for a very long time. There was a breakthrough by the DeepMind team, which many of you may have seen in 2020, where using machine learning and AI techniques, they were able to predict the protein structure that would be produced for a given protein highly accurately in many cases. In some cases, producing results that were not known, experimentally in advance. And so this was very exciting, but I'm told by the experts that this does not mean that the protein folding problem is totally solved. So one example of how it might not be solved, which I guess is kind of interesting, is that if there's some protein that folds in an extremely sort of unexpected way, like perhaps based on some physical mechanism that we haven't really studied very much or haven't seen in experiments much so far, then our machine learning algorithm may not predict this because it's been trained on a data set that just doesn't have this sort of unexpected behavior in it. So it can be sort of interesting to go back to sort of the basics of physics and try to understand what the expected result is of a protein folding without using this sort of initial data that we have. And the approach that we were thinking about in this work is lattice-based protein folding, which is a sort of popular approach in quantum algorithms for protein folding, because even though it's perhaps a sort of very basic, very sort of almost prehistoric approach to protein folding, it is sort of quite amenable to implementation on near-term quantum hardware. And the idea is that we imagine that our protein is living on a lattice, perhaps a square lattice, but in this work we're focusing on a tetrahedral lattice. And this has some sort of physical motivation for how this will look in terms of atomic structure, but also it's sort of relatively straightforward to implement on near-term hardware because we've got sort of fairly simplistic structure. And a conformation, so a configuration of the protein, is represented by a sequence of turns on a lattice. So we imagine it's sort of going along as like a string, and it turns left or turns right. On this figure here, I've just shown a turn-based encoding on the square lattice, but you can also do this on the tetrahedral lattice. And what we're interested in is minimizing the energy, or finding the minimal energy of a certain classical Hamiltonian H. And this Hamiltonian is described by a certain so-called potential function, which in our case is called the Leonard-Jones potential function. And this sort of describes the energy of a given configuration of a protein. And then there's some sort of penalization term in the Hamiltonian as well, which is basically it tries to stop the protein intersecting with itself. So it penalizes configurations which send the protein back on itself, which are unphysical. So we want to find the state effectively that minimizes the energy with respect to this given Hamiltonian, which I'm not going to define in any detail. This is a sort of very abstract picture, but we have this potential which comes from physics, which tells us what the cost is of a given configuration, and we want to minimize that cost. And the idea is we're going to try to solve this using some optimization algorithm. And we were interested in simulating how well QAOA performs for this problem, but it turns out that even for very small proteins, this is not possible on a simulatable number of qubits, so on a number of qubits which you can simulate classically. And we had to sort of cut down the size of the protein that we were considering somehow, and the way that one can do this is by only encoding certain atoms within it and sort of integrating out the other degrees of freedom of like the other atoms in the protein. And this is something which is not a very realistic thing to do, both either on physical grounds or on sort of computational grounds, but at least it enables one to get something which you can deal with using classical simulation. And somehow this shouldn't make the problem any harder for the quantum computer. So if we can find sort of bounds on how well the quantum algorithm can perform, then this should translate to the even harder problem of dealing with the whole protein. Okay, so I just want to mention very briefly a couple of the results. And basically the results in this case are less promising for QAOA, I would say, compared with the case of satisfiability. So we were looking at a very small example, which is so-called alanine tetrapeptide, which is something that fits onto a 20 qubits 20 qubits setup, basically using the technique I mentioned on the previous slide. And the first thing we were looking at is what's the probability of actually producing a solution that doesn't have any clashes, so any of these sort of non-physical intersections of the protein with itself. And we were looking at how this scaled with the number of layers of QAOA. And it turns out that if you want to have a sort of low probability of producing a clash, like 1% or something, you actually need something like 40 or 50 layers of your QAOA algorithm. So that's in the world of near-term quantum algorithms, that's a pretty deep algorithm. And this is for a very small instance size. So that's maybe a bit demoralizing, that even to produce a physical solution with high probability, you need to have quite a lot of layers. But perhaps the more demoralizing thing is to compare the performance of QAOA against classical random guessing. So what this x-axis, this is probably a slightly confusing plot, but what the x-axis is showing is the quantiles of the QAOA distribution in terms of the cost, the energy that's produced. And what the y-axis is showing is basically the number of classical random guesses you need to do in order to produce a solution with an energy that has, to produce a solution whose energy with respect to QAOA is as good. So like, let me take random example. Okay, so for example, this 10 to the minus 3 here. So this is saying to produce something that's in the top 0.1% of solutions according to QAOA, you need, in the case of, p equals 3, for example, you need just over 6 times as many classical samples than you do using QAOA samples. So, for QAOA to produce something in the top, 0.1% distribution, you need like 1,000 samples. And to do this classically, you need sort of 6,000, roughly 6,000 samples. So the ratio between the number of classical samples you need and the number of quantum samples you need is never that big. Like it's never worse than just over 6 or 7. So basically this is saying that classical sampling can match QAOA up to a constant factor in terms of the number of samples. Okay, so just getting to the end, and basically the message I wanted to say is that ultimately the performance of near-term quantum optimization algorithms seems to depend on which problem we're looking at. And I guess most excitingly, random k-sats seems to be fairly promising in that QAOA appears to have some scaling advantage over leading classical algorithms. I should stress that in particular, this means that it outperforms naive use of Grover's algorithm applied to the problem, which would be scaling like 2 to the n over 2, like the scalings we were seeing with best in this. And one interesting thing you can do is you can actually apply amplitude amplification to QAOA, these algorithms that we were looking at. So if you have a fault-tolerant quantum computer and you're happy to have a very high-depth quantum circuit, then you can shave off a factor of 2 from the exponents of the algorithms that we saw here. One thing I should come back to is comparing against other classical algorithms. So we did not compare against some specific commercial solvers like Gurobi. We compared against ones, which were algorithms that, were sort of in standard sort of benchmarking suites or ones that appeared in the literature. We did compare against some other ones which are designed to be good for random SAT instances, and we did not find they work very well. I'm happy to discuss that more if people are interested. And yes, the flip side is for protein folding, QAOA seems to struggle a bit more. And what we found in our sort of small scale experiments is that it might not significantly outperform classical algorithms. Though this was, a small scale SCUD study, I think probably a lot more work would need to be done to, conclude about that. And I guess the last thing I wanted to say is we are currently hiring at Phasecraft in particular to do work on optimization algorithms for quantum computers and related areas. So if this sounds of interest, just feel free to get in touch. That's everything I wanted to say. So thank you.
Okay, thank you very much, Ashley. This was very nice. Thank you very much for a very interesting talk, sharing these new results with us. We have about 7 minutes, more or less, for questions. So let me just make sure I see the participants list. I would invite anyone who wants to ask a question, please just intervene. I think we had, thanks a lot to all who participated. We had about 80 people overall joining. Anyone wishing to intervene, please just go ahead. Yes, please, Ronald. Hi.
Hi, Ashley. Thanks for the nice talk. I have two questions. One is, so the performance of near-term hardware very much depends on sort of the noise robustness of the algorithms. Did you take this into account somehow, or are you assuming perfect quantum hardware for the QAOA?
Yeah, so in this analysis, we were assuming perfect quantum hardware for QAOA. So we were basically interested in the sort of, the scaling on a perfect quantum computer. I think it's an interesting question to understand the performance with noise. One thing that is appealing about these algorithms is that some quantum circuits aren't very deep, and also that somehow it's not the end of the world if there are a few errors, because you're sampling, and you might, for example, be able to produce something that's close to the real satisfying assignment of your formula or something like that, which maybe is still useful. So yeah, I mean, this is basically something else that would need to be done, and I don't know the answer.
And then my second question is, could you repeat how you measure the runtime of the QAOA? You said something like 1 over the probability of finding a satisfying assignment, but that seems to set the cost of the quantum computer to 1.
Right.
How do you take this into account, like the cost of actually running the QAOA?
Right. So the algorithms that we were running, they're all constant depth. So the or even if they. Okay, I guess there's two parts to your question. One is the sort of practical question of what are the real world clock speeds and things like that. And that one, we were just ignoring because we're just thinking about scaling. But then there's also the question of, is there something in the quantum computer which takes a long time to run? And in this case, the algorithm is only, it depends on how you measure the depth, but in the very worst case, it's only going to be polynomial in depth. And the runtimes we were looking at are all, inverse exponential, or the runtimes are exponential. So it's only going to be appearing as a sort of lower order term.
But this is then QAOA after the optimal parameters have already been determined?
This is with fixed parameters that are determined based on a small scale numerical optimization, actually. I should probably have said that a bit.
I see. Thanks.
So yes, so we crucially, we're not assuming the need to do a variational optimization over some parameters, because we sort of get the parameters from some small scale training.
Mm-hmm. Thanks.
Thank you very much. More questions, please. To intervene. So I see there's something on the chat, but there's a private message about the mailing list. Okay, so actually I have just a general curiosity to start with. So you said this work was done in collaboration with the company, or given the motivation of a pharmaceutical company. How do they react, or in general, how does the company react given your experience in Phasecraft when the speed up is maybe not so promising?
I think, in the end, people would like to know the truth, and I think, different. I mean, firstly, the results, about protein folding, different people may interpret them in different ways, and some may have a more optimistic view on our results than others, than we did. But I think that, because even if a particular direction is not the most promising one, at least in our opinion, others may disagree, then there are many other interesting directions in which one might apply quantum computing in pharmaceuticals and other areas, like, for example, direct simulation of the quantum mechanics in the problem, or indeed like molecular dynamic simulation or something like that. So I think that they are happy to know an answer, and I think would much rather know a correct answer, even if it is, perhaps a pessimistic one.
Sure, that's very fair enough. Also, what I imagined, but thanks for confirming this. And thank you, Ashley. I see Jordanis. Do you want to intervene?
Yeah, hi. I don't know how to raise my hand, so I'm raising it like physically.
Okay.
So my question was that, QAOA is a very generic algorithm, right? And we are kind of hoping that it will give you good results for very different types of problems. Like protein folding is not the same as random KSAT, let's say. So if we really want to solve specific use cases, do you think that we would need to actually go back into the algorithm and change the algorithm and come up with new, more specialized algorithms? Or QAOA is what we are stuck with, and the question is, okay, what is the depth, what are the parameters, and so forth?
I think that's a really interesting question. I think for me, for a problem with a lot of structure, I think it seems like a bad idea not to use that structure in one way or another. And this can lead to a bit of a tension, because sometimes this structure is not easy to do, especially on a near-term, to take advantage of, and especially on a near-term quantum computer. I mean, I would say that for problems like KSAT, which seem, like they actually have very little structure to them, then I think an algorithm like QAOA is very promising, tempting to use. But algorithm, I mean, for example, a problem where you're optimizing within some space where you really want to stay in that space and not to, and not to go outside of it, then I think it's going to be tricky to get a good performance with a quantum algorithm unless you somehow stick within at that space, so you ensure at least theoretically you're there. So I think my inclination would always be to try to use the knowledge of the problem as much as you can, but sometimes that can be easier than others. It's not a very good answer, but perhaps it's a general one.
Sorry, I couldn't find the unmute button. I was answering to a couple of colleagues here who were asking about the mailing list on the private chat. More questions, please. So Alexander, I was answering its work. It's fine, but I will finish the chat later. So I think if there are no more questions, and given the time, I would just ask Rafael if she can please share the slides with the announcements for the next session. So besides this colloquium where we invite speakers from outside EXI, and so this colloquia will happen every 2 months, and in between, also with the regularity of every 2 months, we will have the EXI seminar, also open to all, where members of EXI will be sharing their results. And so the first session of the EXI seminar will be a talk by Freek Witteveen from the University of Copenhagen. So that's on Monday, the 17th of April at 5 p.m. Central European Time. And our colleague Robert Koenig from the Technical University of Munich will be the organizer and host of this seminar. We also want to announce the next colloquium in about 2 months' time. So the colloquium will happen on Tuesdays, on the third Tuesday of the month every 2 months. And so we're very happy to announce that Andrew Childs from the University of Maryland will give the second EXI colloquium on Tuesday, 16th of May, always at the same time. Next slide, please. Rafaela. Yes, so by the way, we want to advertise the World Quantum Day, which is taking place on April 14th, but in fact, with events going from March to May around, centered in April 14th. And so last year there were more than 200 events in all continents, so we encourage you to also join this bottom-up initiative if you want. Thanks, Rafaela, for including this. And finally, so I want to thank, on behalf of the AXI team, Ashley, once again for delivering this first AXI colloquium and sharing these very nice and interesting results with us, especially on behalf of our colleague Andris Anvainis, who's the actual organizer of the colloquium, but by a conflict of dates, unfortunately couldn't be here today. And advertise our first AXI workshop taking place in Paris on the 2nd of May. So our website should be up and running later this week, we hope, and then the information will be there. But you can find already this advanced information here. And also there's this Twitter account that Andris set up, so you can also, we will also be able to find information there. So thank you very much, everybody, for joining. It was great to have you in this first session, so many of you from so many different places. And again, special thanks to Ashley for sharing these results with us. Thank you very much. Have a good day.
Thank you very much.
Thanks.
Thank you. Bye-bye.